Okay, we are live on YouTube and the recording is started in the cloud. So let us get started. Welcome to the Silicon Valley chapter of IEEE Computer Society event. I am the chapter chair, Vishnu Pendyala. Ours is the largest chapter in the Silicon Valley section of IEEE, with over 4,000 subscribers in our mailing list and a strong following of over 12,400 on Twitter alone. We are uniquely positioned by the virtue of our location and available expertise, and thanks to the virtual meetings these days, we are able to avail of expertise from all over the Professor Amlan Chakrabarti from University of Calcutta in India. And he will be talking on quantum paradigm for machine learning. The topic is obviously very interesting because we have nearly 200 registrations for this talk, which is really one of the largest registrations in terms of numbers that we have had. And it's a really good start for the new year. The area of quantum machine learning is a young one and is expanding quickly. Quantum machine learning builds artificial intelligence that utilizes quantum technology to increase the efficiency and effectiveness of learning algorithms. In order to overcome the difficulties of merging quantum computation and machine learning and to advance our understanding in this field, strong interdisciplinary cooperation is required. So today's talk's objectives are to introduce QML, quantum machine learning, to the audience and to examine the field scope as well as its technical difficulties. And today's speaker is Dr. Amlan Chakrabarti. He is a full professor in the A.K. Chowdhury School of Information Technology at the University of Calcutta. He was a postdoctoral fellow at the School of Engineering, Princeton University, United States during 2011 to 2012. He has 20 plus years of experience in engineering education and research. He is a recipient of the DST Voice Cast Fellowship Award in Engineering Science in the year 2011, the Indian National Science Academy Visiting Faculty Fellowship in 2014, the JSPS Invitation Research Award in 2016, Erasmus Mundus Leaders Award in 2017, the Hamid Visiting Professorship from University of Cambridge, United Kingdom in 2018, Siksha Ratna Award by Department of Higher Education, Government of West Bengal in 2018, and has been awarded as a Fellow of West Bengal Academy of Science and Technology in 2022. Since his PhD research, Dr. Chakrabarti has been an active researcher in quantum computing logic synthesis, quantum CAD, and quantum algorithms. In his PhD research, he developed strategies for quantum logic synthesis and was one of the key contributors in formulating the nearest neighbor problem. During his postdoctoral research at Princeton University, he contributed to the circuit optimization techniques for the PMD-specific quantum gate libraries, and also in the development of the first of its kind fault-tolerant quantum logic synthesis tool coined as FTQLS. He and his research team have made good contributions to quantum algorithms such as random walks, binary well-led tree, graph coloring, and click problems, which solve many of the important computing problems in the quantum computing domain. In 2021, Dr. Chakrabarti's research group devised the entire ant colony optimization problem in the quantum setting, which was the first of its kind, and this resulted in the award of IBM Quantum Researchers Access Award to his group, and they were the first group in India to receive this award. His PhD students are working in top quantum computing organizations such as HCL, a company in India, Atos, PwC, etc. He's also the mentor of the first quantum startup in Eastern India coined QRD Lab. He has also served in various capacities in various higher education organizations, both at national and the international levels. He has published around 200 plus research papers in refereed journals and conferences and has graduated 20 PhD students. He is the series editor of Springer Transactions on Computer Systems and Networks, the series editor of the Springer book series on water informatics, and associated editor of the Elsevier Journal of Computers and Electrical Engineering, and guest editor of the Springer Journal of Applied Sciences. He is a senior member of IEEE and ACN, IEEE Computer Society Distinguished Visitor, Distinguished Speaker of the ACM, Secretary of IEEE CEDA India Chapter, member of the International Water Association, Vice President of the Data Science Society, and life member of Computer Society of India. His research areas are quantum computing, machine learning, computer vision, reconfigurable computing, and VLSI CAD. So that's quite an impressive profile, and I'm pretty sure we have a lot to learn from Dr. Amlan today in today's talk. Before I turn over the control to him, I just wanted to mention that Dr. Chakrabarti would like to take the questions towards the end. So please post them on the chat window, and I will relay them to the speaker towards the end of his talk. And the links to the video and the slides will be posted on our website in about a week. The talk is anyway live broadcasted on YouTube, and I'll also submit it to IEEE.tv. Assuming that the speaker is comfortable sharing his slides, I'll also post the slides on the website. So with that, I give the control to Professor Chakrabarti. Over to you, Professor Chakrabarti. Please take it over.
Yeah, thank you, Professor Vishnu, and I welcome all to the participants of my lecture today. And I thank the IEEE Computer Societies and Pendala chapter for organizing this. And myself being the volunteer of IEEE, I would always be happy to contribute and to participate in this type of IEEE programs. So let me start my presentation. So today's presentation or the lecture topic is a quantum paradigm for machine learning, and this is really coming in a great way, because as we know, machine learning is a very talked about topic and domain, both in research as well as in industry. And obviously the upcoming of quantum computing, especially in the last 10 years, right, is really exciting, and that gives us the opportunity to leverage the quantum computing infrastructure or the quantum computing resources to work upon this the machine learning algorithms and problem areas. And my today's talk will be focusing upon that how we can use the quantum computing algorithms or the quantum computing systems to solve the machine learning problems in an efficient way. So my lecture has two parts. In the first section, I will just try to set the floor for the quantum computing, because I don't know that what is the background of today's participants. So the first part of my lecture will just give you a very overview of the basic things which are considered in the quantum computing domain. And in the next part of the talk, I will discuss about how we can do machine learning on these quantum computing infrastructures. So as we know that our the computing infrastructure or the computing systems have traversed a long journey. We started with electromechanical computers, And then came the discovery of silicon, or the silicon, and then the silicon chips, which miniaturized our computing circuits and computing hardware to a great extent. And we are all getting a very good value for that, because we are now having very powerful computing engines in our small smart devices, which are 10 times powerful than the computing systems, the computing desktop type of systems 10 years ago. So this miniaturization actually gave us an enormous scope of enhancing the functionality of our hardware, and hence to have more and more functionalities in the software applications too. So we can run now many complex applications in our the smart systems or small computing devices. But as we move forward, our silicon dimensions are now closing down to 1 atomic or 2 atomic layer, right? And so there is an opportunity that whether we will try to exploit the power of the atoms or subatomic particles of matter to do computing. And that is the drive towards the quantum computing. So one of the drive of quantum computing was obviously the miniaturization of the present hardware will automatically lead to the atomic scale of matter, and to exploit the atomic scale of matter in computing. The other drive of quantum computing which was initiated by Richard Feynman, the very illustrious physicist in MIT, who said that around 1980, who said that that means if we are trying to find or trying to look into quantum physics in a better way, working quantum physics in a classical computing system is not the good way of doing the things. The real charm of quantum physics can only be exploited when we can build the real quantum machines, quantum computing machines, which can compute in the quantum paradigm, right? And that was obviously the one of the other drive of building quantum machines, which came from the physicists, that hey, can we just try to look into the quantum phenomenon of matter, and we can just build the quantum systems. But the third drive, which was actually very phenomenal and most popular in the domain of quantum computing, is that can we have an algorithmic speed up, right? And then the works like Peter Shaw, Love Grover, David Deutsch, Richard Joyce, right, and many more came one after another from the late 90s, and still it is going on very strong. And we have found that yes, that means it's not only that squeezing down the size or just trying to look into the quantum physics, we require quantum computers, but quantum computers are required because they give us a very good speed up, okay, for many of the problems which are pretty hard in our present classical computing regime, can have a polynomial or a super polynomial speed up, if not exponential, right, in a quantum computer, right? And that's the journey which has started for quantum computer, and I think that is now picking up in a very fast pace. So what is novel about quantum computing, and what is so special about quantum computing? So when I started my research in 2004 at Indian Statistical Institute at my city in India, Calcutta, so I thought that quantum computer will be that. So at that point of time, I was basically focusing on how we can convert the quantum algorithms to quantum logic circuits, and what are the advantages and what are the challenges in building these quantum circuits. That was the main focus of my PhD. But that point of time, okay, maybe we are just thinking that, oh, quantum computer will be something that the computers which we are using, okay, in a daily life, like your desktop systems, or maybe your okay, laptop systems. But we have understood over the years that the quantum computer will not be like that. Quantum computer will be a resource heavy infrastructure, which will be accessed to the cloud, right? And we all know that many of the quantum computing services are now provided to cloud. Like we have the IBM quantum service, we have the Amazon quantum service, we have the Microsoft quantum service, and many more are coming in the pipeline. So the quantum computer, okay, which is obviously still, still a sort of an experimental setup or a research setup facility in many areas, but it's quite a established technology now in a small scale. Small scale means it is around 200 qubits, and now it's done. We are getting ahead. We are looking ahead to a qubit count of 1,000 or 1,000 and 2,000 within the next 2 to 3 years, right? And the special about quantum computing is that these quantum computers or the basic basic drivers of quantum computing is there are some intrinsic phenomenon which happens in this this dimension of matter, that is the atomic and subatomic dimension of matter, right, cannot be harnessed in the classical domain. Okay, so the phenomenon like superposition, entanglement, and interference, which are the phenomenons and which are being exploited in quantum computing algorithms, are very unique processes which can only be harnessed in the quantum domain, right? And that's why the quantum computing is novel, and from that only the power of quantum computing comes up. So if we just look into the basic understanding of quantum computing, it starts with the understanding of the quantum bits, or commonly known as qubits. So we know that what is a classical bit. So classical bits are the way by which we store the data in our classical computers, and we know that they can have value of 0 or 1. So that is represented in the left side of this diagram in my slide. And if you look into the right side of the diagram, okay, so you will see that there is a representation of the quantum state representation, right, in terms of the block sphere, right? And we know that there are two specific states, obviously, which is called state 0 and state 1, which is equivalent to the logic state. So state 0 and state 1 of a qubit, okay, which is equivalent to a logic state 0 and logic state 1 of a classical bit. But apart from this logic state 0 and logic state 1, we can find that there are other possible states on the surface of this block sphere, which can be represented as a contribution coming from the both state 0, or if I do it as a vector, this vector have a projection on the state 0 as well as on the state 1. So it is a sort of contribution coming from both state 0 and both state 1. And this is the phenomenon of superposition which happens in a quantum system. A qubit is the smallest possible quantum system, right? And a single qubit can also show superposition. So if you look into the surface of the Bloch sphere, right, all the points on the surface of the Bloch sphere, except these two extreme points, 0 and 1, they are all superposition of the two basis states, okay, of state 0 and state 1. So basis state of a single qubit system is state 0 and state 1, but we can have superposition states which are represented as a combination of state 0 and state 1, right? And that is a very, very unique phenomenon in quantum system, and we exploit this phenomenon for the speed up of an algorithm, which I will show next. So if we look into this this particular scenario, so what happens in measurement? So this is a very important question. So suppose this particular Bloch sphere, which comes in the center of my picture, this has a lot of superposed states on the surface of the broad sphere. But what happens is that once we try to do a measurement, which is in the classical domain, right? When we bring the quantum system to the classical domain through measurement, what we find that these states collapse to either the state 0 or either the state 1. Okay. And this is a very unique property of quantum system. So now the question arises is that then how do we do the quantum operations? Because ultimately it will converge to a classical state. So the trick, the quantum game, okay, is that when we try to, before the measurement, right, you do certain quantum transformations. It's also called quantum state evolution. Okay, evolution means with time the quantum states changes, okay, with the operations of appropriate quantum operators or quantum transformations, right? And this evolution of the quantum state will be such that, okay, the probability of one of the states, or maybe some of the states, are made higher, or the amplitude, probability means the square of the amplitude. So actually the amplitude of some of the states are made higher through this quantum evolution process, which can be also described by the quantum transformation through some quantum gate operators or unitary operators, right? And through the transformations, we try to enhance the amplitude of some states, and we try to decrease the amplitude of some states. In a very simple case, it can be enhance the amplitude of one state and actually try to decrease the amplitude of the other states. And this is actually done because we have the quantum interference. So quantum interference can constructively interfere and can enhance the amplitude of a state or multiple states, and can reduce the amplitude of a state or multiple states, which is called destructive interference. And then what happens is that then we try to measure the system will collapse to the highest probable state in terms of the amplitude, because the amplitude square, the maximum amplitude square, gives the maximum probability of the particular state, and the system will converge to that particular state. So the entire game of measurement, as I said, the quantum game, the entire quantum operations or quantum circuits or quantum transformations, whatever we say, right, will lead from a distribution of quantum states to a maximized distribution of certain quantum states, which are probable result states where we want to converge, right? And that's why when we do the measurement, the quantum system will converge to that result state, and we can obtain the result after the measurement. And that's the philosophy of this quantum process. So now let's look into that. That means why quantum computer promises to be powerful than a classical computer. Okay, so the power of computation, which depends on the resources, right? That means you put some resource to your computing system, computing infrastructure, and to gain some power of computation in terms of that is how large a number you can deal with, or how larger the size of the data you can deal with. So in the case of classical, right, if we try to enhance a data size, right, we have to push the equal amount of resources. Okay, if you have to work with a data size from 16 to 32 bits, right, you have to push the same amount of 16-bit resources everywhere, right? Be it in your memory storage, be it in your ALU data path, or be it in your ALU functions, right? You have to add this. So the processing power of the classical computer is linear with resources. But if we look into the quantum computers, right, if we want to work with eight states, right, eight states, we can use 3 qubits, because the number of states what we can generate out of try to remember that you can tell me that, sir, using 3 bits in classical also I can generate 8 states, but not 8 states together, right? The quantum superposition gives you the scope that a 3-qubit system can generate 8 states together and can work on all of these 8 states together, right, due to the quantum superposition. Now, if we want to go to 16 states, right, I just want to enhance the number of qubits from 3 to 4. So normally the number of data elements, right, you can process in a quantum computer scales. Okay, that means it is exponential, okay, with the resources. So with the 3-bit, you can work with 8 data samples, and using 3-qubit, you can work with 8 data samples, and using 4-qubit, you can work with 16 data samples. So this enhancement in the power of computation gives the exascale or a higher scale up in computations in the quantum computers. Now, if we look into that, what is a qubit? And this is still a very ongoing research topic. Many technologies some of the technologies are very well established. Some of the new technologies are still under explorations, and some of the technologies which were existing earlier, people have found that they are not scalable. So there are three main issues when we think that whether a technology we can go ahead in the technology. That means the common technology is already being shown here. We have the superconducting loops. There are a good amount of work and good amount of computing has been developed on superconducting qubits, like IBM, Google, Rigetti, DAWF. They are all working on superconducting qubits. There is an ion trap based quantum computers which are called IonQ. These are also coming up to be very promising, and many of some of the quantum infrastructures are now based on IonQ. Intel is trying on the silicon quantum dots, and they claim that they are quite successful in doing that, right? And there are something called topological qubits. Apart from that, there is a lot of other domains like optical quantum computing, which is phenomenally done for quantum communication, and there are some few more technologies. So when we look into the technology aspect of the quantum systems, one of the criteria is the scalability. Here we can build a quantum system of 5 qubits or 10 qubits or 20 qubits using this particular technology. Can we build a quantum system having 100 qubits to 1,000 qubits or 2,000 qubits, or can scale up to 5,000 qubits, right? Because the scaling up of the qubits actually defines a larger quantum system. And when we define that the quantum system is large, there are effects like decoherence, okay, which can make the quantum property of the system die out fast. Okay, so the decoherence time of a quantum system is a parameter which tells that means how long the quantum system can hold the quantumness properties or the quantum properties of matter, and can sustain the quantum paradigm or quantum phenomenon in the system. Because there is a natural tendency of decoherence for every system that after a particular time, the system will collapse and the quantum properties cannot be extracted out of the system, right? Unless it is reinitiated again. So this is a quantum decoherence, and that also leads to something called quantum noise. So the decoherence means that the system becomes pretty noisy. And due to this noise, you cannot actually work with the system, and the system collapses. So the scalability, decoherence time, and the noisy system are the principal factors, and obviously the controllability of the system, which is a part of scalability, the cost of the system. And these are also needs to be counted. okay, in a specific technology. And this is a technology. So technology research in quantum computing actually is being driven by these thoughts, and that means, and I think that there are a lot of things and are still yet to be done in this particular domain. Now, coming back to very fundamental stuff in quantum computing, that as I said, that the quantum system evolves through certain transformations, and these transformations can be visualized in many ways. The very popular way of visualizing transformations is through the unitary matrix operations. So we have the different types of unitary matrix operations which obeys the quantum laws of quantum physics, which means that each of these matrix transformations are unitary matrix. They have an inverse, right? And the inverse for the unitary matrix is basically the conjugate transpose. So if you look into the dimension of the matrix, they are actually 2 to the power n cross 2 to the power n dimensions, right? And this n means what is the number of qubits on which this matrix can operate. Okay, so if you look into all the matrices, what are shown here, these are all 2 cross 2 matrices. So here the n will be 1. So it means that these all matrices are single qubit operations or single qubit gate operations for the quantum computation, for the quantum computing circuits. Okay, and if we look into the how we try to look into these operations. These operations can be unitary operations like what we show in the in the quantum computations in the right side, right? Like the way we define the truth table operations or the not gate operations, right? Similarly, we have the equivalent transformations in the quantum computing in the quantum computing domain, like the single qubit operators can be defined as a very simple Pauli operation, say Pauli X, Pauli Z, Pauli Y, and the Hadamard transformation. Pauli X, if we try to look into a little bit deeper, we will find that Pauli X is nothing but a NOT operation. It will flip the state 0 to 1 or the state 1 to 0. Similarly, we have the sigma Z operation, which is a rotation operation across Z, and sigma Y is also a rotation operation across Y. Right, sigma X is also a rotation operation across X, but that is actually gives performs the NOT operation. And this Hadamard gate is a very typical gate. The Hadamard gate, what it does, it takes an input 0 or 1, and it prepares a superposition of both the states 0 and 1. So when I give a 0 to the Hadamard, it will make an equal superposition of 0 and 1. When I pass 1 to this Hadamard gate, it will also make the equal superposition of 0 and 1. But in the case of 1, due to this negative sign, what happens is that means for input 1, the Hadamard output is a plus 0 and minus 1 superposition state. So it does a change in the phase. If the input is 1. Similarly, this Hadamard, if we pass a superposed input to this Hadamard, suppose I pass 0 plus 1 superposed state, it will converge it to 0. And if I pass 0 minus 1 superposed state, it will converge it to 1. So these are the very important operators by which we try to handle the rotations, handle the inversion of the quantum state, and try to build the superposition of the quantum state. And these are all single qubit. Okay. Next, there are 2 qubit operations. Also, the most common 2 qubit operation is called the CNOT gate, which is called the control NOT gate. The principle of this control NOT gate is that suppose we have 2 qubits, one is qubit 1 and one is qubit 2. Qubit 1 can be said as a control qubit, and qubit 2 can be said as a target qubit, right? And what happens is that so I hope that I have a figure of this. Okay, I will come to this later. So in the case of CNOT, what we have is that if you have 2 qubits, so one can be defined as a control qubit and one as a target qubit. So the principle is that if the control qubit is 1, the target qubit will be flipped. So target qubit will have a NOT operation. So that's why it's called a control NOT. So the NOT operation only happens when the control qubit is triggered. So the NOT operation happens in the target qubit when the control qubit is triggered, which means that if the control qubit is 1. So if the control qubit is 1, the CNOT gate flips the target qubit, right? And this matrix operator, is fine enough to do the transformation on the quantum state. But this is a 4x4 matrix, so it means that it accepts 2 qubit, as I said, the control qubit and the target qubit. Now, what we can do, we can actually try to represent the. So this is actually a representation of the states. There are different representations of the states, right? If you look into the Hilbert space representation, what we try to do, we try to define each of the state as a column vector. So a single qubit can only be state 0 or state 1, like this, state 0 and state 1, and the 0 is represented by column vector 1 0, and the 1 is represented by column vector 0 1. Now, when we do a 2 qubit state, it is a tensor product or a chronicle product between the 2 single qubit Hamiltonians, right? And this will result to 0 0 0 1 1 0 1 1 states, which will be again represented by the respective column matrices as shown here. Only to just for those who doesn't have a background of quantum computing, just to remind, just to make them understand, is that this particular sign, which is a sort of angular brace, right? This is called the Ket notation. So when we try to define the information in the classical space, we write 0 and 1. But when we try to represent the information in the quantum space, we use the notation Ket notation, and so it is 0 Ket 1 Ket, or 0 0 Ket 0 1 Ket 1 0 Ket, and so on. And now this can be also represented if a state is a superposition state, as I represent in this second row of this particular table, right? You will see that a state psi is an arbitrary quantum state. I can represent a state psi as an arbitrary quantum state, and an arbitrary quantum single qubit state. Arbitrary single qubit state can be represented as superposition of 0 and 1, where C1 is the amplitude for the 0 and C2 is the amplitude for 1. The rule is that the C1 squared plus C2 squared will add up to 1, because the sum of the probability will be 1. So C1 squared is the probability of getting 0, as C1 is the amplitude. C2 squared is the probability of getting 1, as C2 is the amplitude. So that rule also needs to be followed, that C1 squared plus C2 squared will be equal to 1. And then if I represent this in an arbitrary state of C1 0 and C2 0, then it can be represented by a column vector C1 C2. And so on, I can represent an arbitrary 2 qubit state, which is a superposition of 0 0 0 1 1 0 1 1, and I can go on doing this. I can make a superposition of 3 qubit state, I can make a superposition of 4 qubit state, and I can go on increasing this. Okay, now in the operator domain, how the operator works. The operator is a transformation on the state psi. So if I consider that the psi is a single qubit state, psi will be represented by a column vector C1 C2, and U, which is an operator, will also be of dimension 2 cross 2, because n is 1. It's a 1 qubit operator. So the operator will be U operator of 2 cross 2, and this U is a unitary represented by its own coefficients, right? U11, U12 to U22, right? So this is the way we represent, and this U operator works on this column vector, right, and generates a result, and that's the outcome of this operator. And this we can go expanding for larger operators, like this example shows you that how we can do it for a 4 cross 4 operator, which is basically a 2 qubit operator. Suppose the example maybe a CNOT example. So this operator again works on the column vector which has 4 elements, because it's a 2 qubit state. Okay, 2 qubit superposition state can have 4 elements. Okay, so this is the way we can actually try to generate the operator theory of the quantum computation, and we can try to understand that here, starting from an initial quantum state, how we achieve a final quantum state. Okay. So this is what I was telling, that this can be, this is a general lookout. So we can have a input state psi can be represented as, input state psi can be represented as a superposition of 0 and 1, having each of having coefficients of alpha 0 and alpha 1. And once we process this through this gate, we will come up with a change in the amplitude, which becomes alpha 0 becomes alpha 0 dash, and alpha 1 becomes alpha 1 dash, because we have done a transformation of the state psi to a state phi. So psi was your input state and phi was your output state, and the transformation can be okay. It can be modeled in this way, okay? And we can all place the matrices, the matrix of the transformation G, and we can just try to compute that what happened when G was applied to psi, provided we know the values of the coefficients of G, and provided we know the values of alpha 0 and alpha 1 of the input state, right? We can easily compute that what will be the what will the amplitudes, or what will be the state phi at the output. Okay, right? And this I already discussed. These are the matrices, and this is the way how the state transformation works. So this example tells you that if your G is I, or G is X, or G is Y, or G is Z, or G is H, what will be the outcome of phi? Okay, so this is a very well demonstrated, very simply you can just estimate all these operations. Okay, now I'm skip this a bit. So now I will let us look into this particular okay, let us go back a bit. Let's look into this particular just an animated way of understanding how a quantum circuit works. Okay, so if you look into this, we will see that a quantum circuit, this is a quantum circuit where we have two qubits. Two are initialized with 0 kT, and this is a 1 qubit operator, which is a sigma x, which is a NOT operator. And this is a control NOT operator. As I said, it actually flips the target if the control is 1. Control is normally the top qubit, and target is normally the bottom qubit. And then we do the measurement. So what happens is that I start with okay, 0 0. So 0 0 0 0 okay, qubit state is represented by the column vector 1 0 0, right? And after the NOT operation, okay, the first qubit flips, so it becomes 1 0. So the column vector changes. And then after the C0, as the control qubit becomes 1, the target qubit also flips, and the column vector changes, right? And it's not a problem, because we will get all the other amplitudes are 0, and only one amplitude is max is 1. So this measurement will always lead to 1 in the first qubit and 1 in the second qubit. So this is a very simple simple go through of the quantum circuit. Now if we make the things a little bit complex, so instead of a pure 0 in the first qubit, I make it a superposition of 0 plus 0 and 1, right? Obviously to explain it, I can have a 0 at first, and then I can apply an Hadamard here, and then I can get this state. Okay, so now provided I give a superposition state at one input, right, and the other input remains the same, what happens next? So this superposition input, after applying this NOT, the 0 will be flipped to 1 and 1 will be flipped to 0, but overall the quantum state will remain the same because it's an equal superposition. Now what happens after the application of C0, what happens is that if we consider this, because this qubit can be considered both as 0 or 1, right? So if we consider the input of this okay, top qubit is 0, then the output of this, okay, then this qubit and the output will also be 0. But if I consider this qubit is 1, then the output at this qubit will be flipped, so this will be 1. So what happens actually is that means after this particular thing will make the output also a superposition output. So superposition will be okay, the probability of getting 0 0 is half, amplitude is 1 by root 2, and the probability of getting 1 1 is also half. So this is a little bit dicey. So now this is an equal superposition of the states 0 0 and 1 1. So if we try to measure it, there's a 50% probability of getting both the qubit 0 and 50% of probability of both the qubit 1. Now, this is also a special state which I will not discuss now in this particular lecture. It's also called a Bell state, which means by this type of states are not separable. That is, qubit 1 and qubit 2 are not separable. If we know what's the value of qubit 1, you can always tell what's the value of qubit 2 or vice versa. So after knowing all these things, now we know that this is what is our quantum circuit. So in a nutshell, a quantum circuit is something that we have the qubit states at the initial time, qubit states, and then what happens is that all these quantum operators operate on the qubit states and will generate some state distribution, and then we apply measurement operations and try to read out the outcome. Having said so, you have to understand that this particular circuit depth, what we do in the quantum, this circuit depth is actually applied in the time intervals. So what it means is that means the array of qubits are considered as qubit registers, and each of the sequence of gates are operated on successive time intervals, right? And so the quantum register, which starts from an initial state distribution through the time, evolves by the operation of the quantum states, right, and generates a different distribution. And this different distribution is the result distribution what you want, so that the measurement can actually generate the outcome. And this is the entire quantum game. Our motivation for a given quantum algorithm is that what are the probable gate combinations we will use, so that we can start from the initial distribution of the quantum states, defining the setup state of the problem, and we can come up to a distribution of the quantum state where the measurement will give me the measurement, after which, if I apply measurement, the outcome will give me the result or the solution of the problem, right? And to do this, or to plan this sequence of gates in operation over the time, or the time evolution of the quantum state, is actually your quantum algorithm. Okay. So these are this is a very simple stuff of the qubit of the Qiskit representation. If you work with any simulators, Qiskit, QSAR, QASM, anything, you will have the simulator where you can initialize the values of the qubits, right? You can place the different quantum operators, right? And you can also apply the measurements, and you can actually simulate the entire quantum circuit or the quantum algorithm. Though having said so, there's a little bit thought process involved here. Is that like we know in VLSI design also, we start from a very high level description, and then we map into the technology level mapping of the same circuit description to the technology level mapping. So technology level mapping uses certain constraints which are technology specific, and it might that means it might be a different different way the circuit is represented, right? Which is better for technology, okay, which can be mapped directly to the technology per se. Okay. Similarly, in the case of quantum computation also, okay, that means at the preliminary level we can come up with one particular description of the circuit, but when we try to drive it in a specific particular technology machine or a technology hardware, quantum hardware, okay, there will be certain layers or certain stages which will try to convert this particular circuit description to a circuit description which is optimized, or which is the best circuit description considering the great libraries as well as the other constants of the technology, and it will map it to a circuit which is supported by the technology at best. Okay. So this particular process happens whenever we try to map a quantum algorithm to a specific quantum technology or a specific quantum hardware, and this is called transpilation, right? And this is just taken from IBM Qiskit manual. Okay, so I think that I have just in the halfway mark of my lecture presentation. And until now, what I've tried to tell you is that what is the basic philosophy of quantum computing, how we can realize quantum bits, right? How the quantum bits form the quantum systems, right? And what are the way I can perform the gate operations, and we can perform the evolution of the quantum system, right? And what that is how the quantum algorithm, okay, how a quantum circuit reciprocates an algorithm, and how we can obtain the solution of the quantum process to the measurement. So this uh, uh, okay, this will help you to understand the next discussion, what is the quantum machine learning, the topic of today's the core topic of today's presentation. So quantum machine learning is really going very strong, right? If we see okay, if you see the projections by the pioneers like IBM, Google, Intel, NVIDIA, uh, okay, it's really very promising, right? It's really very promising. The infrastructures, the quantum infrastructures are getting enhanced to handle the quantum machine learning problem. And right, and also we are looking forward to the business applications which can exploit the quantum machine learning algorithms. And so the entire domain is very exciting now, and a lot of research in academia and industries are now being channelized in this particular domain. Though there are once we discuss this, we will come to the thought process that it might not be the entire quantum game. It may be a classical quantum handshake, which will be the best possible way to deliver the quantum machine learning outcomes, right? And we see lot of players in this particular domain, okay, who are trying to harness the quantum power for machine learning, right? And there are atomic state quantum computing, there are superconducting and spin state based quantum computing, there are photonics based quantum computing, and in each of the verticals of the quantum technology, we have a lot of okay, we have a lot of companies, a lot of initiatives has been taken. Now, what we try to see is that that means okay, the present quantum computing approach is okay, depends on the conventional quantum computing approach. Okay, defines that we have very strong error-free quantum computer systems, but which is unlikely in the near future. So there are two types of thought process. One is the fault-tolerant quantum computers, which are quantum computers which can give you scalability, but their errors are pretty low, pretty low. So but these are still in the thought process. These are still in the such process that and we are not yet in this particular regime of quantum computer. The regime of quantum computer where we are is called the near-term quantum computer, where it's called the NISQ quantum computing systems, which are called the noisy intermediate state quantum computing. And the noisy intermediate state quantum computing means these are actually small scale quantum computers, right? Small scale quantum computers, maybe 1,000 or 2,000 qubits, right? But there can be some error. The error values are okay. The noise exists. We can actually reduce the noise by limiting the computing time in these quantum computers, and by doing certain repetitions of the quantum operations over time, right? And try to do some sort of average outcome of the quantum system, okay, with a consideration that noise will cancel out in this averaging of the outcome, right? And this is the way the present quantum direction is going ahead. Okay, it's called a noisy intermediate state quantum computer. Yeah. Okay, So now if we look into the so how this machine learning can be thought about in our quantum circuit, right? And how we can try to visualize how a quantum circuit can be trained, right? The understanding of this comes with this particular picture. So I have said that this was actually shown earlier also. So we have the qubit states or qubit systems, which are there, right? And then we have a whole lot of gate layers, right? One after another. And these gate layers actually defines evolves the quantum states. If you look into the quantum states and the qubit scenarios within a quantum circuit, we will find that the qubits are having the complex amplitudes, right? If you look into this, so the quantum state is actually defined by its complex amplitudes of the qubits, which defines the quantum system. Okay, and right, and these are the these complex amplitudes of the qubits defines the quantum state vector of the system at any point of time. When we try to do the measurement, what will happen is that means if these states are all equiprobable, right, it will converge to any one state. But if we try to make one of the qubit states pretty high in amplitude corresponding to the other qubit states, the probability of converging the system to that particular value is pretty higher. So now we can understand that what is the trick. The trick is that that means we have this quantum gate architectures, which if chosen properly will generate a quantum state which actually prefers some qubit measurements compared to the other, right, in terms of the amplitude, generated amplitude by this state transformation, right? And after measurement, we will get those values out of the quantum circuit. Okay, so generating an outcome from the quantum circuit is dependent on the gate operations and its overlap on the measurement. Actually, gate operations generating the quantum state of the quantum state of the system, and its overlap with the measurement operator, which generates the measurement and converges to a particular value. Right? If we understand that, we can try to guess that what we need to do. So these state vectors are represented by psi, as I already said earlier, right? And the circuit can be the circuit can be represented as a parameterized form, which is U theta. And now this U theta is very generic. Obviously, this U consists of multiple U's, multiple U for each qubits, or can be concatenation of U's, across the qubits over the time. So then both combinations can work together, right? I will show it pretty soon. I will show it. So now this conceptualization is called the parameterized quantum circuit, where the quantum circuit parameters are defined as theta, and the proper choice of theta can actually generate the quantum state which is favorable for measurement and can give you the favorable outcome. Okay. So this is a very simplistic view of quantum machine learning, what I show here, right? So what is quantum machine learning? The quantum machine learning is that you have a quantum system which is operated by a sequence of gate parameters, right? And they have been modeled as U theta, right? And you do a measurement, right? And and in the measurement you can know what is your loss and what is how much you deviate from your actual, right? And then you try to define it as an optimization problem, use a classical optimizer, and try to settle down the values of the theta, right? And so that these gate combinations will lead to a quantum state which when measured will have the minimum amount of error in the result, right? Either it is a prediction result or it's a classification result, right? And that's a very, very top level view of the machine learning, what happens in a quantum system. So it's called ANSAS. This is the normal way of defining the parametric quantum circuit. It's a network architecture, right? That means you can tell that, okay, I have a neural network also in the classical domain where we have a lot of weights combined with a lot of node functions, and ultimately we have some sort of nonlinear thresholding, and by which we try to get an outcome. So similarly here also we have this ANSAS the best quantum network, which are parameterized quantum circuits, and we can try to tweak this parameterized quantum circuits in a proper way so that this quantum circuit leads to a quantum state which is favorable for measurement and can generate a low error in its outcome. And that's the way we try to define this parameter quantum circuit defines the particular type of quantum machine learning model we are planning ahead. Okay, so if we look into this, so the one way of defining the parameterized circuit is that I can have the independent qubits, and we can have a sequence of rotation operations on each of the qubits, right? But this might not work always. This is it's better to also do a sort of combination of entanglement and operations, because this entanglement will actually try to couple multiple qubits. So there are two operations in a sequence we need to do. So we can do the parameterized rotation operations on each of the qubit, and then we can have intermediately, we can have entanglement when we have a sort of coupling multiple qubits and trying to make an influence of one qubit over the other, right? And this sequence will continue and will try to generate the quantum circuit what you require, right? Parameterized quantum circuit what we require. And these parameters, whatever the parameters of this theta 1 and theta the theta parameters, these parameters we need to go through an optimization process and need to feed back to your quantum circuit so that the measurement leads to the minimum error, and that is due to the proper choice of your theta parameters. Okay, so we'll come to this in the pretty soon. Now let's try to look into the goals or the functional domains of this quantum machine learning. So quantum machine learning are used in various to do various types of activities. Okay, obviously the major activity is to try to crack the complex problems in your simulation, right? We can have the drug discovery, we can have the material simulations, the molecular analysis, right? All this requires a lot of activities in the machine learning domain, which can be seriously taken in the QML paradigm. Okay, there are certain machine learning techniques. Actually, I am not sharing this work here. We have recently come up with a work which is called the IEEE, which is a quantum error reduction, and this was published in ACM transaction of quantum engineering, where we showed that machine learning can be used to reduce the quantum error. So machine learning in one way can also be used to improve the quantum systems. Okay, so because there are certain known facts of the quantum systems, and if we can use the known facts as our training data, right, and we can prepare a particular prediction model based on our known facts of quantum circuits, right, we can predict certain outcomes of the quantum systems, and we can actually reduce certain make certain outcomes stronger of the quantum circuits. So this is called enhanced quantum computing where QML is also required. Okay. There are certain systems, certain applications where it's called quantum sensing, where we actually try to look into the quantum system as such, right, and try to find out the quantum properties of the systems, because the quantum systems in true actually are implementing these quantum operations in its physical existence of the system itself. So now, can we analyze certain quantum properties of matter, right, and try to understand that how they work, and this is called the quantum sensing, or we can actually try to perceive the quantum machine functions. Okay. There are certain domain of classical applications, okay, where we try to do a part of the classical, okay, maybe the optimization part in the neural network, right, and we can use the quantum as a tool to optimize a certain function in the classical domain. So these are the varied ways how we can take the benefit of the quantum machine learning. Now, in terms of the applications, there are really many applications are there. As I said, the drug discovery, okay, a molecular discovery, chemistry, logistics, transportation problem, right, finance. We can go to risk analysis. So a lot of applications can be thought about in the where quantum, because these tasks are really complex tasks, and these are really challenging in the classical domain. So we can people are using this in the business platforms to solve the complex problem using the quantum systems and trying to prove the quantum supremacy. So if we look into the taxonomy of this quantum applications, we will find that the quantum machine learning applications, we can find that there are two axes. One is the data axis, one is the algorithm axis. We can have the topmost corner is obviously, we know, the classical machine learning. Then what we can have the classical data, okay, quantum data, and maybe the classical algorithm, okay, which also works, okay, right. But the most promising is the classical data and quantum algorithm, which is actually the bottom left corner, and the upcoming where we have the quantum data and the quantum algorithms of machine learning. So as we know that in case of machine learning, we have data and models, or data or process, right. So we can have two variants, and obviously we will focus presently. Our focus is mostly on the classical data, right, and quantum processes of machine learning. But quantum data and quantum process of machine learning are also coming up in a pretty good way. So let's look into the problem one by one, that how we try to look into the machine learning, how we handle the machine learning problems in the quantum domain. So we know that machine learning problems can be considered as a supervised learning problem. So the supervised learning problem, what we have is that we have a training data set which give you the labels which are already obtained from the domain experts, right. We train the model using the feature space and the label, right, and the model learns, right, and tries to generate an accuracy which is pretty high considering the training set data, right. And then what we have, we actually try to test the model. So if it is a classifier model, we can suppose we have trained the model using the class labels, some of the shape class labels, right, and then we provide a subset of that as a test data, right, and we try to see that how accurately the model classifies the test data, right. If it classifies pretty good, accuracy is pretty high, we are guaranteed that okay, this model is doing good, right, and can work with any data. Now, if we look into the scenario in the quantum domain, actually this transformation of the data to the feature space is the key in the machine learning, right? And in the classical way, we also do a kernel transformation, which transform the data into the feature space in a good way, such that the next level of classification, right, or maybe the prediction can work well. Similarly, we have a kernel space in the quantum. So in the quantum, the kernel space is governed by the Hilbert space because we are mapping the data from the classical domain to the feature space, which is in the quantum domain. So any quantum domain system, right, will be defined in the Hilbert space, as I shown earlier, right? It will be defined by the Kate algebra, right, in a Hilbert space. And so this mapping needs to be done, and is called the quantum kernel, right? And once we do the mapping, right, this mapping actually is a nonlinear mapping, right? And this nonlinear mapping can result into a very complex scenario which was there in the data space to a simple scenario in the quantum feature space. So for example, that means the data space, maybe the points very close to each other, and maybe we have a nonlinear separation in the data space. And this nonlinear separation in the data space can actually, by this kernel trick in the quantum space, can actually convert it to a linear problem, right? And then in the quantum space, the measurement, okay, if you try to measure, the measurement can itself give you a very good answer, because the classification has been done in a linear space. Okay, the linear space has been achieved, right, in the kernel, to the kernel operations. So now if you look into here, what happens actually is that we try to first is the feature space encoding, which is actually the kernel trick. So we do the kernel trick of the feature space encoding, right? And we try to we then try to prepare this entire feature space in such a way, okay, such that the measurement operator, okay, gives us the result of what is expected, right? Expected means that suppose I am training, suppose I want that, okay, these are the features of level A, right, and the outcome should be A after the measurement. Okay, so we need to first of all, okay, because these operators can only be applied when we try to push the data into the quantum, okay, quantum Hilbert space. So first we push the data into the quantum Hilbert space, which is a feature space mapping from the data space to the quantum space, right? And then we try to operate on this particular parameterized quantum operations. Okay, these parameters are similar to hyperparameters what we use in our classical machine learning, right? And these parameters, some may be parameters, some may not be parameters. So this is just a representative gate circuit, right? Right, you can have a mix of parameterized gates and non-parameterized gates, right? And this quantum operations on this Hilbert space will lead to a measurement probability, right, which is expected in this particular domain application, right? And that's all the quantum game. So this is the similarity. So this is the expectation value. So in the measurement operation, what we get an expectation value of a particular state. So we should we should have the, if you are doing the training set, we will have the expectation value after measurement close to what is there in the label in the training set for this particular data, right? And for and once we settled on the parameters of the particular circuit, the test for the test data also, the measurement or the expectation value should produce a very close result. Okay, so in order to do all these things, what we need to understand is called the variational quantum circuits, or called VQC, right? So what we saw here is that in the case of supervised learning, as the training data is available, we can actually transform it to the Hilbert space, and then we can compute it in terms of the parameterized operators, and then we can push it towards the measurement. And the measurement or expectation value should be same as that, or very close to as that of the label which is defined in the training set, right? And in the entire process, we have the processing can be done in respect to parameterized quantum circuit. So now what happens is that we will have a preparation of the initial state, right? And then we try to define a quantum circuit which is set by the parameters, right? And then we define a measurement operator. A measurement operator is basically an expectation value of a particular state. Suppose you are doing a classifier, you are trying to do a measurement of the expectation value of a particular level, right? Whether it is high or low. So the way we do it is that the parameters of this particular ux theta operation, x comes from the data, right? And theta is the intrinsic parameters of the gate. Okay, try to remember this is a generalized representation of this entire operation, because there are two parts of it. One is the data itself is a parameter, because if we change the data, the ux theta will change. The outcome of ux theta will change. So there will be two parameters. One comes from the data, which is okay, which comes from your training data, right? Another is the theta, which comes from your optimization, which is your model parameter, right? And then what you do as in the training data, we can always try to define a cost function, which is y minus fx theta to the power k may be 2, k may be 3, k may be 4, defining how we define the loss function, error value, right? And then based on this, we will try to update the theta, right? It can be a Gaussian descent problem. I'm not discussing it now. It can be a Gaussian descent type of problem where we try to modify the theta I minus 1 to theta I, right? And with this theta, it is expected that this error cost will be reduced, right? Once it goes in a reduction, you have this variational quantum circuit a model done, right? And it is expected that means, and if your training set is quite a good demonstration of your domain, right? You are likely to get this done in your for your test data also. Okay, in the unsupervised algorithm, unsupervised algorithm basically, which is called clustering algorithm, what we try to do, we try to generate the same feature space with again a kernel trick, right? Not getting into details of the kernel trick. There's a kernel trick, and then we try to find the overlap between a centroid state and a particular state, which you try to tell that whether this comes under this centroid of the cluster centroid, or it is on the other cluster centroid. Suppose we have certain clustered center states, right? And we try to generate a measurement operator which tries to define that how close is a particular state, right? Because everything is now in the Hilbert space. All the states are in the Hilbert space now, right? And you have defined some of the states as the centroid states, right? And we try to find the overlap of the other states on these particular centroid states with a sort of distance metric, which we tell in the classical domain. Here it is some sort of overlap operation, or we try to take an Euclidean distance with which is defined by this operator. Okay, right? We can actually find the distance between the two states, and then we can actually try to find and using a Grover search. I didn't define the Grover search algorithm. Using the Grover search algorithm is a search algorithm which tries to find an element which gives the ES value for an oracle. Okay. Corresponding, we give a list of elements. Right. The element which gives the ES value for the oracle will be the outcome, right, of your measurement. Okay. So using the Grover search, it tries to identify the least distant centroid of the data point in that particular Hilbert space, using a sequence of quantum operations, right? And the measurement value will give you the particular the value is high or value is low, right? And you can do it, and the good point is that you can generate all this in the parallel, because as you know that in the quantum system we can generate the states in a superposition way, right? And we can always do this operation in a parallel, right? And that speeds up the entire clustering process what we have okay, in the quantum domain, corresponding to the classical process what we do. So we can we can actually generate the states in a superpositions way, and then we can try to do a sort of entanglement between the centroid and the specific measurement and specific state, and we can try to find how close they are, and based on that we can assign the cluster of a particular state. Okay, right. And this is how we can do the unsupervised the quantum algorithm. Now, obviously, the next thought process should be the quantum neural network, right? And we know that in the case of quantum neural network, we also can visualize this as a parameterized form. We can have the theta, which is similar to the weight vectors, right? And we try to do a measurement which will try to do a sort of scaling operation what we do in the thresholding of a nonlinear thresholding operation what we do in your neural network can be the measurement operation, can be a thresholding operation, because it collapses something and it maximizes something, because depending on the probability it will collapse some data, it will make the probability 0, and it will make certain probability very high. So it is a similar to a squashing function. So what we can do, we can actually do this iterations over and over. So we can use a measurement which is similar to the alpha, and again we can prepare the state, right? And again we can prepare the weight vectors using a new u theta parameter, right? And then we can actually go on doing this particular operations and iterations, and can result to the similar thing what we have in a quantum neural network. Okay, right? And from this we can obviously extend it to the CNN also. The only thing is that in the case of CNN, we have a special operation called pooling, which is actually a subsampling of your outcomes, right? So the poolings can also have an equivalent operations, which poolings means that you are trying to select some of the qubits and others not. So you can do a controlled operation on some of the qubits, right? Which means that you are actually selecting those outcomes only, and you can make a quantum channel of the qubits, okay, where the controlled operations, which is a sort of selection equivalent to a selection operation in the pooling, right, can be channelized to the next layer of your convolution parameterized quantum circuit operations, right? And in this way you can actually develop this quantum neural network model, right, using a state preparation, okay, parameterized quantum circuits, which defines the convolution kernel of the weight functions, and then we can have a controlled operations which works as a selection like pooling, right? And this process can go on, and you can come to a particular fully connected network again, and then we can apply a normal neural network type of process, parameterized circuit, to maximize the probability of a particular class, or can be type of softmax probabilistic, like a softmax we have a in our CNN. We can also build that type of measurement type of operations in your quantum domain, right? And these are what I tried to explain is the basic way of visualizing the quantum neural network model in terms of parameterized quantum circuit, right, in terms of the feedback what it gets, right, and to tune up the parameters, and how it can look into the supervised, unsupervised, and then the basic philosophy of how we can develop a similar type of operations and neural network and convolution neural network in a quantum setting. So I think I end up here. So my conclusions to this particular talk will be that obviously QML has a quantum machine learning has a huge application in the coming years, right? That means we know a lot of business enterprises are showing great interest. We are connected and we're connected to some of these problem domains from some of the enterprises, and obviously this is really going to be a great exploration in the next few years. The models, the number of parameters, right, how to adjust for large sample sizes, for large problems, right, is still a little bit consideration. We require more understanding and more research in this particular direction, and the work is going on. So high dimensional space, how we do the feature reduction, which is very common in the classical machine learning. We do a feature reduction and feature selection process in the classical machine learning, how we will do it in the quantum state. These are also some of the open problem areas here. The last one is obviously the noise resilience, because still we are working in the NISQ regime, and we are trying to work with smaller spans of the quantum circuits, and once we have the larger scale of quantum circuits, how the noise will come up, how the noise will affect our measurement, because our quantum neural network is heavily based on the total tuning up from the parameterized quantum circuit to the measurements. So how the NISQ effects will be working on this quantum machine learning models. This is also a food for thought, that whether we will lose out the quantum supremacy due to these noises in the QML needs to be well researched, and we need to progress a lot in this particular domain. So last but not the least, I just want to introduce that this entire work, what I showed, is not only my sole work. It's a work of my students, my group. Right, we have a strong group at our School of Information Technology, University of Calcutta, quantum computing group. We work on the quantum CAD, quantum algorithms, quantum machine learning, and quantum cryptography. And we have students who are final year PhD students and got good positions in industry already, and also some postdoctoral students who are joining us. And so I thank you, I thank you once again for inviting me and giving me the opportunity to present this lecture. And now I'm open for questions.
Yeah, thank you, Dr. Amlan. It was really very insightful. In fact, we have quite some appreciation on the Zoom chat and also on YouTube. The YouTube live video already has, I think, 7 likes. And there are some questions as well, quite a few interesting questions as well. I will probably first read those questions or interpret those questions. The first question is, very excited about quantum computing. This would probably impact about blockchain technology. Probably can be sustainable without environmental damage. So I think the question is, how sustainable is quantum computing and its relation to blockchain? Would you like to address that?
Yeah, very good question. Actually, that means quantum, the quantum process or the quantum blockchain is one of the activities which have started. But in terms of general cryptography, actually, quantum has a lot of potential, and I feel that quantum cryptography and quantum communication is moving faster than quantum computation, right? Because the quantum cryptography, as we know, that the QKD, the quantum key distribution, is actually a very well established technology, though it is still within a short distance. But people have, due to its cost and due to availability of the quantum channel, which are optical channels, but they're experimentally achieved in many of the laboratories and many of the industry. A quantum random number generator is now a business product. Now many of the cloud services are now offered or will be offered pretty soon, based on the quantum random number generator, where you can use the quantum random number generator as your key sources for your classical cryptography. Secondly, in terms of the quantum teleportation, which is also a bit costly still now, but quantum teleportation gives you a very absolute security of teleporting the data from from any point to any point, provided you can have the communication with a quantum source, which is called a Bell state generator. So these are some of the things which are very well engineered applications are now present. But in terms of real implementation, obviously one is the cost, and other one is that how we can make a pure quantum channel in long distance communication without the other interference from the environmental cause. And these are still a bit challenge, but these challenges are less compared to the challenges what we have in large scale quantum computing. So I think the quantum communication, quantum cryptography, and quantum security is actually, though I didn't touch it here, but there are a lot of works are going on. Yeah.
So in terms of sustainability, how sustainable is
sustainability,
this?
Yeah. Sustainability in terms of quantum, the quantum is a process. I didn't also touch that. It's a reversible computing, as you know, fundamentally. So what happens is that, as you know, the phenomenon of how we lose energy in computing is that each bit lost at the output is a loss of energy. But in quantum computing, we can do a perfect reversible computation. So loss of bits are not there. So we have a reduction in the energy, provided that means in the quantum regime. So it is in terms of computation process, it's a far more sustainable than classical computer. But still the challenge, as we know, the challenge is on the qubit system itself, because we need a lot of energy to cool down the system and to put it into that particular state. So those are the issues which are a little bit on the higher scale of energy, but just to maintain the quantum state. But if you look into the quantum operations per se, that is very energy saving operations, and that is also one of the drive of quantum computer, that can we do reversible quantum computing in the real environment. If we can do that, that will be really a thing to go for sustainable computing.
Okay. And the next question relates to what you touched upon a little bit. What about its impact on cybersecurity?
Yeah, I said that with cybersecurity, people are really going at a high speed in cybersecurity. In the quantum computing, quantum number generators are already available. That means it's commercially available. Quantum key distribution is also commercially available. Quantum teleportation is a bit costly, but it is there available in the small scale. Some of the countries have already reported that they have done large scale quantum computation, but it needs to be well validated also. That is, I think, it's very promising. Quantum cyber and quantum internet protocols are coming up. We are forming a research group on quantum gateway. This will both for quantum communication and quantum algorithms. So this is very promising. Yeah.
Yeah. So the next question is, actually there's a lot of interest. So there's a lot of questions. I hope you'll have time to answer them. So the next question is, please comment between how far is the gap between research and industry coming to the market. So basically they want to know the gap between research and industry coming to market.
Yeah, gap is there. It's undoubtedly there is gap, but what I can see for the next for the past 5 years, if you observe, and if we just try to extrapolate this to the next coming 3 years, I will see that the gap is decreasing very fast. Okay, that means now enterprises are at least speaking about that how we can generate a sort of use case on quantum computing, right, for the business problem. And also people are generating proof of concepts on some of the business problems on quantum computing. Rolling out at scale at the business is also, I think, will be That means under pipeline in many of the organizations are trying to offer that. There are a lot of quantum cloud services are now being offered by a lot of pioneers. So I think that obviously there are teams, and I also have seen that there are teams which are being built based on the quantum algorithms, and quantum computation groups are now being built by a lot of this enterprises. So I think basically the logistics, the finance, the pharma, these are the problem areas where the major business drive is there in exploiting quantum computing.
Okay, thank you. And the next couple of questions seem to relate to how to get up to speed with quantum computing. So the question is, which is the best online server to practice quantum computing? And can you suggest any book which will be best for studying quantum programming?
Yeah. So quantum book, that means I think if you are really want to get into quantum computing, the Bible is the book of Nelson and Chuang. It's a quantum computing book, by Isaac Chuang and Nelson. That you should, I think that is from Cambridge University Press. Right, you can find some new editions. There is a fantastic lecture by David Deutsch, that is from Oxford, available online. Right, you should listen to that. And there are also lectures of Peter Shaw, Love Grover in the internet. In terms of practicing quantum computing, obviously there are tools from now. Quantum has been incorporated into your tensor library also, right? If you look into the libraries of IBM Qiskit, QSARC, they are well incorporated quantum libraries are there, right? You can start with them, and there is also a tool which is done by some of the research labs, right? You can look into that, and I think there are a lot many, and also Amazon have a bracket tool which is also available on cloud. So these are very good tools where you can experience and you can practice and you can develop your quantum. They will give certain for simulation. I think entire thing is free. If you want to run this on the real quantum hardware, there will be a cost associated. For some qubit size it's free, but for higher qubit size it's for the business application. So it will be you have to that means it will be cost. It's some cost you have to pay. But I think for simulations, most of the tools are absolutely free. Yeah.
Okay, the simulator probably runs on general purpose computing, right?
Yes. Simulator runs on general purpose computing. Perfect. Yes.
Yeah, and the other thing is, I believe IBM provides free quantum computing to some research institutions.
Yes. So IBM has a research access program. You can connect with the IBM group, and you can try to find out how much free access you can do. There is a quanta of free access for all, right? And over that you need to make a special request, and you need to have a special consideration in terms of your research problem. The IBM will selectively give you this access.
Okay. And the next question from Sayan Day from IIT Kalyani. He's asking, what will be your suggested path to get into QML? He's interested in machine learning, quantum machine learning.
Yeah, that means you can connect me later also, but there are a lot of research papers are there, right? Phenomenal research papers have been come out in quantum machine learning. Basically, the first thing you have to understand the kernel trick. If you understand the kernel trick in the quantum machine learning, that is the most, that is how we operate in the Hilbert feature space. That's the most important part of the quantum machine learning. If you understand that, and then you can actually work with a lot of quantum machine learning problems.
So that made me a bit curious. When we talk about this transformation to Hilbert space, are we talking only about the quantum kernel machine learning, or does it apply to all of quantum machine learning?
This is basically the quantum kernel machine learning, which is the most easier, which is the most easy to understand and most widely popular. As you rightly said, there are also some other forms of quantum machine learning which are also being done. But I think the kernel is I like the kernel trick most. Okay, so I prefer that particular path of machine learning.
Okay, so the similar kind of thing that we do in support vector machines applies here, like the kernel function defines the distance between the points.
Right, and it helps the measurement, and it actually directly helps the measurement and how you map it.
Okay.
And it generates nonlinear to a linear. It converts it to a linear problem in that particular space.
Okay, and simulators are available for quantum kernel machine learning, right?
Yes, they are available.
Okay.
QSVM is very popular. You can just try some of the libraries of QSVM.
QSVM.
Yeah.
Okay. The next set of comments, I think, are appreciation from Deepankar Chatterjee. Thank you, sir, for your wonderful lecture. Dr. Ajanta Das, it's a very interesting and educative lecture. Thank you, sir. And Vanita Agarwal is asking, is quantum machine learning a better option for image recognition as compared to CNN, convolutional neural network?
Yeah, see, that means at present scenario, we don't have the quantum machines which can go at scale like the image processing we do in the classical. But if we consider that we will have the quantum machines at scales, okay, which is required, okay, say 2000 qubits, okay, or more. Obviously, then the quantum image processing will be much more better than your classical, because you can actually use a lot of these transformations like your interference and superpositions and can generate better algorithms. In fact, one of my PhD students have done some good work, okay, Dr. Sanjay Chakrabarti, who has done some good work in this application, that how we can apply the quantum algorithms for image processing filters, right? Because they work on a nearest neighbor analysis. We didn't implement it, and in research probably we didn't work with this quantum CNN still. But what we have seen that if we can encode the image in a quantum domain, right, and the nearest neighbor operations, what we try to do in the image kernels, okay, it can be well done and can be simultaneously done in the quantum domain, okay, because the entire neighborhood can be represented as a superposition, and we can actually apply the same function on the entire neighborhood on O1 time, right? And then we can measure it, and then we can find that whether it is an age or something or not. So in this way it is better, right? But CNN also people are working. I didn't work with quantum CNN still now, but there are good results of quantum CNN also on image, provided the quantum resources are at scale, right? You can probably beat the classical image processing. That means in terms of your computational time.
Okay. And the next question, I believe, I don't see a lot of activity on Stack Overflow. So is there a community or newsletter I can follow to be updated in this area? And also would be interested in open source projects and general activities.
Yeah, that will be good. That actually that means IBM has a lot of newsletters. Actually, many that means IBM and Microsoft have their newsletters on quantum. But I will definitely try to look into that. What are the good newsletters are there? And obviously there are there are open source projects. Yeah, that means there are open source projects which are there are a lot of competitions and a lot of projects are given by IBM, right, in their sequence of their programs they organize for the community. You can look into that. And similarly, I think Microsoft and Amazon is also coming. Amazon is coming up, I think, with a same sort of program very soon. So you can look into Microsoft, Amazon, and I think IBM, right? And you can get a lot of things there.
Okay. The next question. Please also suggest some of your suggested resources to learn about QML.
Yeah, that means, yeah, Shayan, you just connect me. I will surely pass on to my my research paper. That means the research materials what I used for this particular lecture. There have a lot of archive research documents I have used. I will surely pass it, and I will also pass it to Professor Vishnu also. Okay, that means I didn't put the reference here. Okay, so that the participants can look into the reference. I will send you a reference list maybe within a few hours today, right? So that you can push it to the interested participants, the reference list for this particular lecture, right? And those are very good reference lists you can use.
Yeah, that sounds good. So I'm moving on to YouTube now. So there is a comment or question from Sujit Day, and he's asking, sir, whether decoherence factor can be completely removed.
This is a very difficult question, because completely removed we are not. That means I think nobody have thought about this in the quantum domain. The technology we need to have, the only because what happens is that this particular states in this subatomic layer are very feeble states, right? And we are strengthening the states with some external control, and we are trying to hold the states. But after the qubits, okay, goes with certain operations or certain transformations, right? Within a particular time interval, there is a high probability that they will decohere, due to the physical nature of the quantum system, with the interactions what they have, right, in that particular level of matter. So I don't think that we can make the decoherence zero, but obviously the technology, there are two paths we are progressing. One is that whether we can have a computation which is before the decoherence time, and after the decoherence time we can do a restart, and we can again reinitialize the qubits, and we can start computation. This is one path. Another path is that whether that is the NISQ, what is happening is that whether we can generate multiple experiments on quantum, and which will have different errors, and then we can take an average, and then the decoherence error can be cancelled out. So there are two paths which are mostly taken now. Okay, obviously, if there is a technology which is a longest decoherence time, that is obviously preferred, like superconducting qubits, right? They are still preferred because they are much low decoherence time. That is much better in decoherence in terms of the quantum dots, because quantum dots were very highly preferred at one point of time, but now it is going down because it has a high decoherence. Yeah.
Thanks for that answer. And then there are a few more on the YouTube. These technologies may be good for remote sensing data analysis, as the data is very huge. That's the comment from Dr. M.M. Rao. I think you agree with that, right?
True. Yes. That's a very good point. Yeah, for large data space, okay, you can prove the quantum supremacy better compared to classical. So quantum supremacy can be more established. It's true. This is a very true point.
Okay, and there's also a comment from Iqbal Nadiadi. Good session. Thank you for the presentation today on QML. And the next comment is, talk is very interesting. Another comment from Dr. Ramesh Babu Nukala. Quite interesting talk. Noise is the bottleneck in both neural networks and quantum computing. Hope more research is happening to minimize the same to have potential benefits from QML. So that's just a comment, I believe. So I think we kind of ran out of time, and really appreciate you staying back a little late than what we thought, Dr. Amlan. If it was an in-person event, I would have presented a plaque, but in the absence of that, I would like to present you with this certificate, which I'll share on the Zoom. So this is a small token of our appreciation for your lecture today. It was really very insightful, and thank you so much again. And hopefully we'll stay in touch for any future events and activities. And thanks everyone for attending.
Sure. And participants, Professor Vishnu, participants can have my email, official email. If they have any questions further, they can connect me through email. No, I will be fine to answer those.
Yeah, I'll convey that to everyone who reads that.
Sure. Thank you, Professor Vishnu, once again for organizing this and for hosting me. Thank you.
Thanks a lot. Thanks, everyone.
Thank you. Bye. Take care.